Good evening. Thank you all for joining us. I am happy to welcome you tonight. And before we get started, we would like to acknowledge that founded in 1889, the University of New Mexico sits on the traditional homelands of the Pueblo of Sandia, the original peoples of New Mexico. Pueblo, Navajo, and Apache since time immemorial have deep connections to the land and have made significant contributions to the broader community statewide. We honor the land itself and those who remain stewards of this land throughout the generations, and also acknowledge our committed relationship to Indigenous peoples. We gratefully recognize our history. With that, I would like to bring up our Vice President for Research, Ellen Fisher, for opening remarks.
Hello, everyone. I'm going to do just a couple of things that are more of a historical perspective to a certain extent about the ARL because it is the 70th anniversary of the ARL. And I want to just say up top that ARL is the highest honor that UNM honors faculty with in terms of the research scholarship and creativity. And so it's kind of like UNM's version of a Lifetime Achievement Award. Only most of the time people are not dead or even emeritus. They're still very active researchers at UNM when they receive the award. I also want to point out that the ARL recognizes research and creativity. And so over the years, the ARL recipients have spanned across more than 30 different departments. Some of the departments include art, music, English, linguistics, communications, and journalism, business, American studies, and the list goes on and on. Would anybody like to guess which department has had the most ARL recipients over the last 70 years? Okay, that's a good guess, but not right. And that's a biologist speaking. Anybody have any thoughts? Any other guesses? What? Not fine arts? No. Not pharmacy? Physics. Okay. Actually, the two that are tied at the top with 6 each are anthropology and physics. So that was pretty cool, right? The next highest, just to give Tom a little credit, the next two are also tied. It's biology and psychology, and they're both tied with 5 each. So I did a little history. I looked back and looked over all 70 awards. And so so a couple other additional fun facts here. According to my team, because we were asking what kinds of fun facts could Ellen throw out here at the beginning, and that prompted someone to say that there are only 2 talks with any humor in the title, according to my team. But we hope that there was more in the actual lectures, and Edel, we're going to be looking to you to provide some humor as well, okay? Also, I want to just say a couple things these are just really, it's kind of fun to think about it. In the inaugural year, that award went to Professor Leslie Sphere from anthropology, and the title of the talk was Some Aspects of the Nature of Culture. Okay. Just to point out, that individual in 1945, he founded the Southwestern Journal of Anthropology, renamed the Journal of Anthropology, it was renamed to the Journal of Anthropological Research in 1973. And then in 1967, the Leslie Sphere Distinguished Professor of Anthropology chair was established. So this is somebody who had a really good influence starting way back. And again, the inaugural recipient. The other thing I thought was pretty cool in looking over the recipients was that we see these names every day as we walk around campus. Stuart Northrop from geology was an ARL recipient. William Parrish from business administration, France Scholes from history, Edward Castetter from biology, Frank Logan from psychology, and Victor Regner from physics. And so all of those are buildings on campus. If you didn't recognize them, you need to get out more from whatever building that you're holed up in. And I'm going to say a couple of topics that I thought were interesting titles. So Scholes, since my office is in Scholes Hall, the Spanish Conqueror as a businessman, a chapter in the life of Hernando Cortez. That was 1957. Mind, Eye, Hand, and Stone was 1976, Professor Clinton Adams from Art History and Photography. I mean, you guys know our photography program is world renowned. Let's see. Dialogue with the Dead, Mummies, Monuments, and Malqui. That was 2003 from Professor Jane E. Buxta from anthropology. This one I love because the very first person I met, almost the very first person I met from UNM was Barbara McCready. And the title of her talk in 2018 was Till Death Do Us Part, a lifetime of research to better understand and treat alcohol use disorders in the family. And then a couple of other notable that I wanted to point out. The very first woman to receive the award, the very first one was given in 1954. The first woman to receive it was in 1988, and that was Ellen Goldberg. Again, I thought that was good because her name's Ellen. My name's Ellen, for those of you who didn't catch that. And that she was from microbiology, and the topic was genetic basis of sexual expression. And then lastly, another one of my favorite authors, Rodolfo Anaya from English. The title of his talk was Aztlan, A Homeland Without Boundaries. And the last little fun fact that I threw out here was that in the year I was born, a chemist, and I'm a chemist, received the ARL. So there's all kinds of connections to be had if you just look for them in the ARL. But with that, I just want to say that it is one of the highest honors that our university gives. This year's recipient is equally, if not more so, worthy of the honor. And I'm really looking forward to his talk. And with that, okay. Okay. Who am I introducing? Oh, yeah. So Steve Graves is going to come up and give a few remarks too, the Associate Dean for Research in the School of Engineering.
Yeah. So it's with great pleasure that the School of Engineering is happy to congratulate Professor Shirmaglu on the annual research lectureship award. Edel is a distinguished professor in electrical and computer engineering, and it's really he's played an extraordinary role in the School of Engineering over the years, over his long career. Most notably, recently for me, he's my predecessor as the Associate Dean for Research, where he did at least 7 or 8 years of outstanding yeoman's work of growing the research in the school immensely and with great foresight. But beyond that, this is about his research, and he's internationally recognized for his work in pulse power, microwaves and directed energy, and importantly, he's helped build UNM's international reputation in that area to the point where we're really well known. And one of the things that I really am proud about being considered an engineer is that we do real world things, and Edel has done real world things, and his work has had real impact. He's impacted both the institution and how it's been built, and plenty of students, many students I've seen success from his students, but also like the Directed Energy Center and things of this nature. He's been outstanding, and so his impact has been extremely large. He represents the kind of scholar, that not only elevate the field, but has elevated our institution. And he's very much a source of pride and an example of research excellence at UNM. And his technical distinction and leadership has been admirable over the years. And so School of Engineering is very thankful to have him. And I don't know, I know that he's got longtime colleagues that will actually do a much better job with more detailed introductions. And so our next introducer is Christos.
I don't know if I need this, but I will use it. I do? Okay. All right. So now I know why I have to introduce, after listening to Ellen, is because I'm 70 years old, and this is the 70th. So now finally I figured it out. Can you guys hear me? Because I cannot hear me. Thank you. All right, so I've been friends with Edel for 26 years. I'm gonna give you different aspects, not just research or some other things, just to see the complete person that Edel is. Most people think engineers are dry, they have zero talents. Only the biology folks are really that smart. But anyways, today, it may be true for some of us, but not for Idel. Idel is special. So I want to start by saying where he was born. So Idel was born in the Bronx, New York, and he received his PhD degree from Cornell University. In 1988, UNM was very lucky to have him here join us as an assistant professor. And he started as an assistant professor, but now he's not only distinguished, he's super distinguished. And for 37 years, he never stopped being a role model for all of us. So in terms of research, Idel is considered today one of the top, I would like to say the best. Sorry, I know there are some people there that may be getting hurt, but I'd like to say the number one out of 8 billion people on earth. That's huge. So, but he really is. So that is good. Especially in the area of high power microwaves. Idel has 4 books, but I really think 2 of them are the good ones. And those are considered, one is in high power microwaves, the other one is high power microwaves and sources. And he, had both of those in 1 decade, and both of them are considered the Bible in each area. So one guy, 4 Bibles, 2 Bibles. So that is amazing in 1 decade. So there is not a single student researcher anywhere in the world who works in high power microwaves that doesn't reference those books. It's impossible, so that's why we call it the Bible. So he got a lot of funding over the years, over $55 million. And of course, his funding came in from the Department of Energy, DARPA, Los Alamos. I can't really say all those things because it's a long list, AFRL, Navy, and of course, private industry. Idel had over 800 and I think more now because you keep adding on your numbers there, scientific publications and over 12,000 citations. He has been recognized internationally. He's a fellow of 3 societies, the American Physical Society, the IEEE, which is the Institute of Electrical Engineers, and the Summa Foundation. So on top of all this, he's not only a fellow of 3 societies, he's a jolly good fellow as well. So in terms of teaching, Idel really has built, there's 4 really big programs in the area of high power microwaves. So Idel has one of them. So, it's very well known in terms of graduate student funding, etc. Very difficult to build these programs because the labs, if you ever see the labs, and I'm assuming you'll show some of your facilities, very expensive to build. So Idel is amazing. And of course, in terms of graduate student and education and mentoring, he had over 40 masters, over 40 PhD students, and we keep counting. He's got a whole lot more students in the pipeline. I know Stacy's here, one of the last ones, and very good. In terms of service, Idel really has done a lot of things. When you reach that status, you're editor, you're associate editor of a lot of journals, and they ask you to review proposals at Los Alamos, San Diego, the LDRDs. He's currently serving as the senior editor of the IEEE Transaction Plasma Science. But I would like to mention that he was a co-PI on an NSF sponsor project, the Engineering Research Visioning Alliance. It's really a group that is setting the future of engineering research in our country. We got one of ours here, UNM, as a member of this. So, of course, he served also as the special assistant to the provost for the relationship with all our labs. He's a director of the AFRL UNM Directed Energy Center here. And of course, as I said, serves in many committees. I have worked really with Idel when he was the Associate Dean for Research. And what I liked about Idil, because I lack that skill, he's got amazing organizational skills. I have zero, and I always relied on him, and he made me look good. And people said there is nothing on earth that can make me look good. But Idil, I think, did something there for me. So he built some very good relationship with Sandia, with AFRL. We had in this room, special day, AFRL folks will come in, tell us some of the programs that we want us to join, etc. But now I would like to talk about Idil, the human being, not the researcher, not the educator that he has excelled. I want to show you some of the other areas where he excels. So first of all, Idil has gotten, did you get 3 Muri Awards, multi-university? 5. So, and this is a lot of money working with a lot of universities, but Idil has engaged and had, a lot of faculty. Even I benefited from this. Even one of our former presidents benefited at, working with Idil on these ones. Idil can play the piano. I don't know how many of you have ever, heard Idil play. He likes music by the Beatles and Elton John for some reason, but he can play the piano. He can play the violin a little bit. I'm not so sure how well, but the piano definitely is very good. What Idil pisses me off with is the fact that when I go jogging or I go to the gym, I have to have headphones to listen to my Spotify. This guy, the music is already, stored. He can run without anything. And that's much cheaper, than what I do, and probably, better quality. So it's amazing. So he also speaks 4 languages. First language is Tatar. So his heritage is from some Crimea, somewhere there. Second one, English. Third one, Russians, that helped him deal with Russian scientists in that area. And Turkish. He practiced Turkish with his wife because, Elmira, his wife, is from Turkey. So this is amazing. Another skill that he's got, he's a wine connoisseur. If he sniffs a bottle without looking at the label, or if he looks at the color of your wine glass, or if he tastes this, he can not only tell you what kind of wine you're drinking, but which region of the world is coming from. So that is amazing. I think he can make more money with this than Pulse Power, He has really traveled over 33 countries. That's huge, because when you go see other countries, you get to see other people's cultures, you get to understand humanity, and it's always good to escape from this Tri-County area where we are, So, but I would say that the greatest accomplishment that Idil has, and of course with Elmira, is that they have a daughter who also got her PhD from University of San Francisco neuroscience. To me, the success of your kids define you to some extent. So this is huge. Congratulations. She's also a postdoc now in University of Denver. And I'd like to say that your success is inspiring, Idil. What I cherish the most is our friendship. Thank you for being my friend for 26 years. Not sure we have another 26 years, but thank you. With that, I'd like to welcome Idil. All right, you got what, 10 minutes?
All right. Can you hear me? Okay. Very good. Well, thank you. I'd like to, first of all, thank Christos for having pushed and nominated me. For that, I'm indebted. I'd like to thank the Faculty Senate Research Policy Committee for selecting me. Again, I'm indebted to them. I'd like to thank Ellen and OVPR for their support and putting on this event. So thank you all so much. All right. So, modern pulse power came to being in the 1960s. Its point of genesis is in the UK, in a laboratory called AWRE, Atomic Weapons Research Establishment. You can think of AWRE as the Sandia Los Alamos of the UK. And then that technology came to the US. Its epicenter became Sandia National Laboratories in the 1970s, which is when the Pulse Power Sciences Center was founded. So this presentation will sort of explain my journey, how I got here and everything. All right, so we'll start with some basics. What is pulse power? What is a plasma? And what is fusion? So, okay, I see the graphics are strange. Pulse power is the science and technology of accumulating electrical energy gradually and then releasing it very quickly in short bursts. Power is energy divided by time. So if you take the same amount of energy that you stored slowly, but then you release it in a very short period of time, you get high instantaneous pulse power. So this technology came to be in the 1960s. The founding father can be attributed to Charlie Martin, J.C. Martin from the UK. And I'll say a few more words about him. Many of you have seen this image before. This is a time-integrated photograph of the Z machine at Sandia National Laboratories. It's the world's most powerful pulse power machine. It is 33 meters in diameter, and it's 80 terawatts of electrical energy. And they use that electrical energy these days to basically drive what's called a Z-pinch. I'll say a few words about that. And then they can generate 350 terawatts of X-rays. All right. In the early days, when I first came to New Mexico in 1988, the Pulse Power Sciences Center was focused on ion beam fusion. But then in the 90s, it was realized that they're not making enough progress. It's a very hard problem. And that's when some of the successes that took place at Sandia on wire array Z-pinches led Sandia to change the name of the machine from PBFA2, Particle Beam Fusion Accelerator 2, to Z simply. And it's Z because it's a Z-pinch. Current flows in the Z direction axially, and then the self-magnetic field causes a compression. So this is an example of a wire array. It's about the size of the thimble, and it's basically 78 tungsten wires that are in an array. So this is during the preparation process. These days, they don't use really wire arrays anymore. They use gas puff, other technologies. But in the early days, in the mid to late 90s, this was the technology. So imagine all that 80 terawatts of electrical power flows through these 78 wires. So what happens when all that power flows through these 78 wires? Well, first of all, the wires start getting warm. The wires start getting hot. The wires explode. They form a plasma. All 78 wires, the plasma coalesces into a cylinder. And then the self-magnetic field, due to the huge currents, causes it to crunch, so it compresses. And the idea is, in the middle of that, you would put let's say, a deuterium-tritium target, and you would basically compress that target and generate fusion reactions. So if you've heard about the successes at Livermore on the National Ignition Facility, NIF, where they achieved the burning plasma in 2022, in NIF, they use lasers to do that, to cause compression. And the alternate technology is at Sandia, it's pulse power technology. And I can tell you pulse power technology is about a factor of 10 less expensive than the laser technology. So this is a plot put together by Jerry Onis. Jerry was the director of Pulse Power Sciences Center in the 1970s here at Sandia. President Reagan tapped on him to be the chief scientist for Star Wars, the Strategic Defense Initiative. And those of you who know Jerry know he's a good scientist, but he's also a adept at marketing and selling. So this is a plot he put together that showed, notice that the numbers align amazingly. So the red is computer power in teraflops. And so he's basically making the argument that the X-rays that they're generating using a Z-pinch is tracking Moore's law for computation. So, very, very wise. So what's a plasma? So plasma is the fourth state of matter. Imagine you have water. If you freeze it, it's a solid. If you heat it up, it's a liquid. If you heat it up further, it's a gas, it's steam. But then if you really heat it up, the outer electrons separate from the molecules. So now you have an electrically conducting gas. That's what a plasma is. And because it's an electrically conducting gas, a plasma can be affected by electric and magnetic fields, all right, whereas neutral gas cannot. Our sun is a plasma. All the stars are plasmas. I took my very first plasma physics class in 1979, and we used the first edition of Francis Chen's book. And in the first page of that book, it says 99% of all matter in the universe is in the form of a plasma. Today, if you look at his third edition, he says 99% of all visible matter is a plasma, because since the first edition, we learned about dark matter and dark energy, so you can't say 99% of matter is a form of plasma anymore. All right. So finally, what's fusion? Most of you saw Oppenheimer, the movie, and the first atomic bomb made during the Manhattan Project is a fission bomb. So basically, you're taking a heavy matter like uranium, and you're splitting it. And what ends up happening is, if you use Einstein's equation, E equals mc squared, you calculate E equals mc squared for that whole uranium mass. And then if you break it and you have two pieces, calculate E equals mc squared, it's less than the original whole mass. So there's a deficit of energy, and that deficit of energy ends up being the nuclear explosion. If you saw Oppenheimer, you also saw Edward Teller. I actually met him in person twice, once at Columbia, once at Cornell. And Teller was the big advocate for the hydrogen bomb. He didn't want to work on the fission bomb. And of course, that's how Livermore came to being. Edward Teller was able to convince the government that they needed another lab to build, fusion bombs. So, of course, in a fusion bomb, you put together light isotopes like deuterium and tritium. And again, when you have E equals mc squared of the two light nuclei, and then you combine them, there is a deficit of energy, and that's where the fusion reactions leads to the hydrogen bomb. So of course, that's an uncontrolled reaction. So what we like to do is, in the laboratory, imagine you have, again, this is an old image, it's from 1998, but imagine you have these wire arrays here, and then in the middle you have a pellet of deuterium tritium, you cause a compression, and you create fusion energy. Okay, personal journey. So I'm going to start with basics. Basic number one is, I know I have a strange name. People are totally confused about me. They don't know who I am. They don't know where I'm from. They don't get it. And then when I start talking, I don't have an accent. That really confuses them. Now, I'm used to it, all right? I've been dealing with this since I was a kid. In kindergarten, my kindergarten teacher asked, who knows how to spell their names? So I'm one of like a handful of students out of 20 that raised my hand, and I spelled it. And she said, wrong, go home and learn how to spell your name. So it's okay, you have to have a thick skin, and, you go on. So my parents are from the former Soviet Union. So the region is called Tatarstan, and that's roughly speaking that red region here. But there are people really all over this yellow region. So my father was born in the city of Ufa here. My mother was born in the city of Penza there. And there must be something in the water in Ufa because there are some famous artists who came from Ufa. If those of you who are older know the famous ballet dancer from the 1960s, Rudolf Nureyev, his partner was Margaret Fontaine. He's a Tatar from Ufa. And the leading Carmen today in the opera scene is a mezzo-soprano. Her name is Aygül Ahmetshina. She's a Tatar from Ufa. So yeah, there you have it. And so if you notice here, there's a river that flows through that region. It's called the Volga River, but the Tatars call it the Idil River. So my dad should probably have spelled my name, I-D-E-L or I-D-I-L. But to him, he was a recent immigrant to the US and he thinks Idil is E-D-L. That's how I landed with this name. All right. So my dad came through Ellis Island in 1951. He was in the Soviet Red Army in World War II. He survived the 900-day siege of Leningrad. If you've never heard of the 900-day siege of Leningrad, look it up. And after he survived the 900-day siege of Leningrad, he was parachuted into the German zone. He was captured. He was in this stalag, and he was able to escape. And when he escaped, he was captured by a Soviet patrol. And my father was an anti-communist, anti-Stalinist. He did not want to go back to the Soviet Union. So my dad manufactured his last name to make it sound like a Turkish name. So Şamiloglu is a manufactured name that my dad did. His original last name was Akhtamov. And I had asked my father when I was older, why didn't you revert to the family name after you came to the United States? And he said, this is the name that saved my life, and that's why he kept it. My mother was born in Penza, as I mentioned here. And my mother's father was a fur trader. And he had traveled all of Asia. My grandfather had been to Japan, China, Korea. So he traveled all of Asia and he knew the land there. So you can see here, my family seems to have this aversion to the communists. So when the communists came in 1917, my grandfather took the family from Penza and went east. So my mother was born in 1922 on the border of Russia and China on the Amur River in the city of Blagovenchensk. So this is a photograph I took from the flight track. I was flying from Tokyo to the United States, and it captured the city where my mother was born, Blagovenchensk, and Harbin, the city she grew up. So my mom actually lived 35 years in China, and then when Mao was coming down, the family went to Turkey as refugees. So my mother's family went to Hong Kong and then took a ship through the Suez Canal and landed in Istanbul, 1955. And then my dad got his citizenship, went to Turkey and met my wife and got married. And then my brother was born a year later and I was born the year after that. So as Christos mentioned, I was born in the Bronx in the shadow of Yankee Stadium. My father got kicked out of 5th grade during Stalin's, because my father's father owned a cow and they were called kulaks. So my father was kicked out of school, so he only had up to partly 5th grade education. My mom had diphtheria when she was in middle school, so my mom didn't finish 8th grade. So my older brother and I are the first in our family to finish middle school, high school, college, and get a PhD. My brother was a professor first at Indiana University, then at University of Wisconsin-Madison, South Asian languages and cultures. And about 10 years ago, he retired from Madison and moved to Astana, Kazakhstan in Central Asia, where he became the founding chair of Kazakh and Turkic languages. So my brother has a second career. So what are the roots of my program? The roots of my program are gas lines in the early 70s. I just got my learner's permit, and because of the Yom Kippur War in 1973, the Arab countries embargoed oil from the United States. So I remember standing in line for hours just to fill up on gas. And I said, this is totally ridiculous. I said, it's totally ridiculous that we're dependent on foreign oil and that this is, there's got to be a better way. So I went to Bronx High School of Science. I went to a good elementary school, Public School 70 in the Bronx. I went to a horrible junior high school. Let it be said that I was there 2 years because I skipped 8th grade. I went from 7th to 9th. I went to the bathroom once in 2 years. The first time I went, and I never went to the bathroom again. And if I had to go to my local high school, which is Taft High School in the Bronx, I would have been killed. I'm 100% convinced I would have been killed. So I had to find a way out. So I had two paths. One is I auditioned at the High School of Performing Arts. If you ever saw the movie Fame or the TV series Fame, it's modeled after High School of Performing Arts. So I auditioned and I got in. So I had a safe backup. And there are 3 public schools in New York City that are by exam. They're free, but they're by examination. One is Bronx Science, one is Brooklyn Tech, and then there's Stuyvesant, which is right by the Twin Towers. I barely, what's important is you have to get above the bar. I got it. I wasn't a lot above the bar, but I was sufficiently above the bar. And, that enabled everything. In 1974, I read this Popular Science article. I still have a clipping of it. And it's about fusion power. And again, remember, I'm complaining about oil and gas lines, and I said, there's got to be a better way. And as soon as I read this article, that's it. A switch went off my brain, and I'm going to work in this field. So that's how I got into where I got in. So the Bronx was burning in 1975, so my father got us the hell out of the Bronx. We moved to Yonkers, which is in Westchester County, bought a house, and these are my classmates, Neil deGrasse Tyson and George Yancopoulos. Most of you know Neil, and some of you might know George. So when Trump contracted COVID in 2020, there was no Moderna vaccine, there was no Pfizer vaccine, but the company Regeneron, George's company, gave Trump the cocktail that saved his life. So I'd like to say at this point, this is a billionaire, a millionaire, and an academic. So again, remember, I'm laser focused. I know what I want to get into. I want to get into plasma physics and fusion. So I was an undergrad at Columbia University in the School of Engineering. And I went to the director of the plasma physics laboratory, Bob Gross. He was one of the big influences in Maya. And I told him, I want to work in the lab. And he sent me down to the supervisor. And just like that, I got hired. Initially, you don't do many things that are interesting. I was basically sweeping up after graduate students. But as the months went by, I got more involved. And I ended up working on a heterodyne measurement of turbulence on a tokamak. My advisor at Cornell, Dave Hammer, he's still not retired. He's probably 82 or something. But he and I got along very well. He was the second main influence in my career. He would have problems with some of the graduate students in the lab, and he would lecture them on how many hours are there in a week if you sleep for this many hours. And he never did that with me, just everything was fine. So we got along. So the main thing is I learned how to tackle a problem from beginning to middle to the end. So my PhD dissertation was basically building this 3-meter plasma, highly magnetized plasma, using a Z-discharge technique, and then using a pulse power machine to generate a ring of protons. So you have rotating proton rings, and they fly through the plasma. And when the protons fly through just vacuum, they go pretty much at constant velocity. But when they go through a plasma, they slow down because they generate a type of Alfvén wave, a magnetohydrodynamic wave. And so that was my dissertation. I I'm very proud of it. Sometimes you see students languishing and they cobble together different things and that's their dissertation, but mine had a beginning, a middle, and an end. So I felt very good. That's me in my Cornell Gratz office, and some of you may recognize that. That's Bruce Springsteen Born to Run poster. All right, so how current events can impact one's career. So in May 1987, I was all set. I was supposed to take my PhD experiment and go to Los Alamos as a postdoc because I was going to merge my rotating proton rings propagating through the Z-pinch plasma with a compact toroid plasma to stabilize it. Well, in the summer, President Reagan announces that DOE will no longer invest in alternate concepts fusion, and for magnetic fusion, they will only invest in tokamaks. So my postdoc went away. The group I was supposed to go to Los Alamos fizzled out. And I was trying to think what I'm going to do next. But 2 weeks later, Professor Stan Humphreys at ECE UNM calls me and says, hey, I'd like you to give a talk. He knew me from conferences and we would always talk. And I remember my wife and I had been to New Mexico in 1985. We were in Santa Fe at a compact toroid workshop. We loved Santa Fe, we loved Los Alamos, and we stayed at a dive on Central in Albuquerque. And I remember neither one of us liked it. And I remember I'm leaving to go give a talk, and she said, tell me we're not moving to Albuquerque. Tell me we're not. And I said, don't worry, I'm just going to give a talk and just going to go. And lo and behold, it turns out to be a faculty job, not a postdoc. And that kind of, and I was, fretting on my flight back. How am I going to tell her, But she took it very nicely. She said, okay, that's fine. Let's go give it a try. And, yeah, so that the rest is history. Okay, so usually if you're an assistant professor, you do research on what you did for your PhD. I couldn't do that because there's no funding in what I was doing. But I was fortunate, there were 2 professors at Cornell who were the founding fathers in the US of the field of high power microwaves. So here's the interesting story. My PhD advisor, David Hammer, was also a PhD student at Cornell in the 1960s. And his advisor was Norman Rostocker. And Norm sent him to spend a year with Charlie Martin in the UK. So my advisor, Dave Hammer, learned how to make the pulse power machine that they had there. So he came to Cornell and they built a pulse power machine like that to generate electron beams. So he was interested in studying how these electron beams propagate through gas, with applications being for fusion. But John Nation, who used to be at Imperial College before he came to Cornell, he did the math. He saw that you have this capability now to make a megavolt electron beam with 10,000 amps of current. You multiply the two, that's 10 gigawatts of power. And then John Nation said, well, if you could only convert 10% of that to microwaves, that's 1 gigawatt of power. That's huge. I mean, back then, the best out they were making were tens of megawatts. And so I was 6.5 years at Cornell. So I sat through brown bag lunches, seminars, dissertation defenses. So I knew everything about high power microwaves. That's not true. I knew enough to write a proposal. And I knew, of course, AFRL here in Albuquerque had a program in high power microwaves. So for my PhD, I used pulse power in positive polarity to make proton beams. All I had to do was get a pulse power machine and make negative polarity and generate electron beams. So that's how I got into high power microwaves. And this was at our laboratory's 50th symposium in 2017 with Chuck Wharton. Unfortunately, both Chuck Wharton and John Nation passed away last couple of years. Okay, let me say a couple of words about directed energy. There are two flavors of directed energy. You have lasers. Everyone understands lasers. They've seen Star Wars. They've seen Star Trek. High power microwaves, no one really understands because it's invisible. You don't see it, and you don't know if it does anything. This is the Thor machine, tactical high power responder, operational responder. And two of my PhD students were the technical leads, Chris Leach and Michael Lambrecht. They pulled this together. And in fact, the high power microwave source that's in there is a clone of Chris Leach's PhD research. I'm not going to say very much about this, but this puts high power microwaves in perspective. This is a plot of frequency versus peak power. And the high power world is up here. You can see gyrotrons used to heat fusion plasmas are here. Basically, when you have the highest power levels, you have the lowest duty cycle or repetition rate. You can't sustain such high powers for a very long period of time. You do it for a burst of shots, and then that's it. I also mentioned this. This is a photo. My daughter and I, during her spring break from college, she also went to Columbia, joined me in London, and I asked her to find and take a photograph of this bench for me if she could. And there is a bench opposite the flat where Charlie Martin used to live, and it says, "In memory of J.C. Charlie Martin, CBE." CBE is commander of the British Empire. If you were an electrical engineer in the United States in the 1940s, 1950s, you would study all of this. You would study Child-Langmuir diode, you would study slow wave structures, you would study antennas, that's what you studied. But then something happened that totally changed the electrical engineering curriculum, and that is the transistor was founded. Once the transistor was invented, all these subjects went out the door, and we have electronic circuits, materials and devices, so on and so forth. And as I mentioned, in the 60s, modern pulse power was founded, and then you have this lineage of high power. So whereas the traditional electrical engineer were the owners of this technology, it's the plasma physicists who are the owners of high power microwaves. And the reason is simple. The currents are so high in these relativistic beams that you have to worry about space charge effects. And that's what plasma physicists do. They know about beam wave interactions. All right, so the original phase started in the late 60s. The original players were the US and the Soviet Union. No one else was a player in the high power microwave world. This is a photograph of the Gamma accelerator in the Institute of High Current Electronics in Tomsk. It's still there. That was the largest high power microwave machine in Russia at the time. This was the largest in the United States. It's called Aurora, and this no longer exists. This used to be in Harry Diamond Labs in Adelphi, Maryland. It was scrapped. So then the period 1985 to 1991, remember I came to UNM in 1988, is the period of Mikhail Gorbachev, and you have glasnost and perestroika. Glasnost in Russian means transparency, and perestroika means restructuring. And of course, the Berlin Wall came down, and I don't know how many of you read Tom Friedman. He's one of my favorite authors. He's an op-ed columnist for the New York Times, and he wrote a column in the 2000s that bookends this phase in US history. He says 9/11, 1989 versus 9/11, 2001. Of course, 9/11, 1989 is 9 November, whereas 9/11, 2001 is September 11th. But he said that period of, in hindsight, that period of time in US history was a loss, terrible loss. And of course, this guy was station chief in Dresden when the Berlin Wall fell, and he was calling Moscow saying, "Hey, we need help, and no one answered the phone. And his maniacal thing, I think, all emerged from that when he was in Dresden. Okay, I was afraid this wouldn't show. So in 1990, again, I came to UNM 1988, three scientists, Chris Christensen, who founded the well-known pulse power program at Texas Tech University. Art Gunther was the governor's science advisor. He was also chief scientist for AFRL. And Jim Thompson. Jim Thompson just was the dean of engineering at UNM when I was hired. And Jim was Chris's former PhD student at Texas Tech. So the three of them went on tours of laboratories in Russia. And then they wrote this article, On the Road. On the Road is a famous series of movies that Bob Hope and Bing Crosby used to do. And of course, this doesn't show. All right, this is, again, it's messed up. This is Gennady Mesiets, who was one of the 11 vice presidents of the Russian Academy of Sciences. And it turns out that Chris, Art, and Jim knew him because of joint interactions and conferences. And so he came to the University of New Mexico. Why did he come to UNM? Because Jim Thompson was dean, he knew Jim. Chris came from Texas Tech, and he knew Art, who was at AFRL. And so he offered to sell an accelerator to the University of New Mexico. So if you remember, in August of 1991, there was a putsch, a coup against Gorbachev. And then Yeltsin was on the tank in front of the parliament, which is called the White House, but the parliament building. And so my trip, I was supposed to go to Russia. My trip got canceled because of the coup. But then the coup ended, the trip got back on. So I traveled to, that's me, I traveled solo to the city of Tomsk, and these are my Russian colleagues. Why did I study Russian? Because my parents used to talk to each other in Russian when they didn't want us to understand what they were saying. It used to piss the hell out of me. So first chance I had to study Russian was in high school. And at Columbia, I was the only engineer in the advanced Russian class. I was the only engineer, everyone else was a CIA State Department wannabe. And this is an announcement of my seminar, which was packed. Okay, so I was there October 1991, so I was strictly speaking in the Soviet Union. The Soviet Union ended in 31 December. And this is the accelerators, the Sinus 6. Sinus stands for Silna Tochki Uskarita, which means high current accelerator. And a footnote in history, so the AFRL gave me money in the form of a blank check up to a certain point. And at first they said, don't tell anyone the Air Force paid for it, don't tell. But then when the accelerator arrived in my lab, they asked, why aren't there any Air Force stickers on the accelerator? And the person who did the paperwork importing this was Susan Eisenhower, the granddaughter of the president. So in 2001, Christos is our new chair. He came in 1999. I was told I had to leave the building I was in. I was in the engineering annex building, but they were going to tear it down to build the physical plant building. So CHTM had pulled out of ECE and they built a building across from the pit. So Christos engineered the ability to make the space in where the CHTM clean rooms used to be usable. So that's when we moved. And this is Senator Heinrich, who came to visit in 2017. He's the, many of you might not know this, he has a master's in mechanical engineering from UNM. He's the founding member of the Directed Energy Caucus in the Senate. And he worked at AFRL as a contractor to Fiori Industries. So he understands pulse power. He pointed to me and says, oh, this is this, that is that, is that. Anyway, and our group became more prominent, and we were at the cover story. I told them, don't call it an E-bomb. They called it an E-bomb. I mean, it's all marketing. But these are the two accelerators in my library. This is the Sinus accelerator. It's a workhorse, still functions every day. The technology that I used to have was a machine that Sandia had given me called a Nereus pulse power machine. We could fire it maybe 4 or 5 times a day, and then inevitably something would break. And with this, my students were able to fire like 600 shots a day. So we were able to take a lot more data than anyone else in the country. So I said there was this power derby, and then in the 90s, what happened is the field became more international. And the big sea change was that our computer codes became so much better. And again, I apologize for the graphics, but so usually up until the mid-90s, your computational folks would simulate a device, your experimentalists would take data. Inevitably, they wouldn't agree. The computationalists would tweak until it agreed, and then great, it agrees, but then they do another clean set and there's disagreement. Well, this is the first time, and this is our paper This is the first time that a particle and cell code and experimental data a priori agree, because we were able to figure out the problem of why. And it was actually Brendan Godfrey, the gentleman at AFRL who gave us the funding to get the scenes exam. He was also evolved into a computational plasma physicist, and he developed the algorithm in particle and cell codes to beat back numerical noise. Footnote, Brendan Godfrey was a student of Wheeler at Princeton working on gravitation, so he's an academic brother of Feynman. All right, 1997, the Air Force organizes this symposium in Edinburgh. It's called, the purpose is to bring Russian scientists and American and European scientists together. It was a very nice period of time. We all worked together. The Russians were getting funding, and we collaborated. I had a very rich collaboration from 1992 until like 2001, and then no more. So our contribution at this time was trying to understand why does pulse shortening occur? Pulse shortening basically means is you have a long pulse electron beam, you generate microwaves, but after a short period of time, even though the beam propagates, you get no microwaves. And we did a laser interferometer measurement inside our high-power microwave device, and we were able to observe that if you have more plasma in the device, you have shorter pulses. So we explained that. In the 2000s, Michael Fuchs joined my program, and he pushed me to get into magnetrons. It's happened to me many times in my career where someone would be a naysayer. When I was a PhD student, I was explaining to a research faculty that I want to have this plasma, I want to fire a beam into it. He told me it will never work. He said the plasma will go into the pulse power machine and short out the diode. I made it work. I figured it out. When I got the Stevens accelerator, they said, what are you going to learn that the Russians haven't learned already? Well, we did learn a lot. We did learn. We were able to figure things out that the Russians had not yet figured out. So the relativistic magnetron was invented by George Bekefi. Another footnote, George Bekefi was a professor of physics at MIT, and my colleague Ivan Deutsch did his undergraduate thesis under George Bekefi on free electron lasers. So people say, what are you going to do that George Bekefi didn't do? Well, George Bekefi achieved an efficiency between 25 and 30%. And when I say efficiency is how much electrical power you can convert to microwave power, about 30 efficiency. Again, to save time, we demonstrated 70% in experiment. We generated 63%. And we proposed the scheme to generate over 90% efficiency. So yes, we were able to contribute. And this is a review article I wrote with two of my PhD students, Dmitry Andreev, Artyom Kuskov. And again, footnote, Dmitry is the son of a previous PhD student I had, Andrei Andreev. Okay, we got into metamaterials. Long story short, this structure that you're looking at has negative permittivity and negative epsilon. So basically, a half wavelength this big shouldn't fit in something that's smaller than this. A half wavelength that's this long needs a waveguide that's this long. We generated a half wavelength of this in a structure that's that, and it's because of the double negative characteristics. And most recently, we got into multi-wave PWTs. I'm not going to get into this. I've had a very successful collaboration over the past 7 years with a group at Technion, Yakov Krasik, and his team, including John Leopold. And they're getting funding from ONR Global out of London, and we were getting our ONR grant. And we've been collaborating and advancing magnetrons to higher frequency. So what goes around comes around. So this is me in 1991 in Vice President Gennady Messias' flat. You can see all over the place, there's vodka, Crimean sparkling wine. This is Michael Yolanding playing guitar. Sergei Korovin was my closest friend. Unfortunately, he passed away in 2006. I was chair of the IEEE Nuclear Plasma Sciences Pulse Power Science and Technology Committee. And in 2012, we had an ICOPS conference in Edinburgh. And I had the pleasure of giving Academician Messias the Marie Curie Medal, which he had won. And in I don't remember what year, but for his 80th birthday in 2016, his former students put together a book for him. It's called Rytzar Nauki, and Rytzar means knight, K-N-I-G-H-T, so the Knight of Science. And I was invited to write an article. I'm the only American with an article in that book. All right, just to sum things up, I've been supervising. It's actually up to 44 PhD and 44 MS. You've seen this before. I want to highlight 3 students, and all 3 happen to be female, and it's the reason I selected them is because they align very nicely with the title of my presentation. This is Kelly Hahn. Kelly Hahn is from Albuquerque, New Mexico. She went to El Dorado High. She took undergraduate electromagnetics with me in the 1990s. She did very well, and I recruited her to work in my lab. She worked in my lab. If she hadn't worked in my lab, she wouldn't have done a master's. If she hadn't done a master's, she wouldn't have done a PhD. So she did her PhD at Sandia. More importantly, she has excelled me. She moved from Sandia to Livermore in 2016, and she measured the neutron yield on the famous shots, the burning plasma. So she's a co-author on the Nature article, and she's a co-recipient of the 2022 American Physical Society John Dawson Award for Excellence in Plasma Physics Research. Another student I'd like to highlight is Sarita Prasad. I met Sarita in 2002. I was invited to give a talk at Nagaoka University of Technology in Niigata Prefecture in Japan. After my talk, Sarita comes up to me and says, I would like to do my PhD with you. And Sarita is a very interesting case because she's originally from Fiji, and she went to Japan to study engineering. Before you can study engineering in Japan, you need to learn Japanese. So she spent 2 years learning Japanese in Japan, got her bachelor's in Japanese, did her master's in Nagaoka University on a high-power microwave device. And then I had told her, I encourage you to apply, and and she came. And so she finished in 2010. She worked at Raytheon, Sandia Labs, but most importantly, she founded IMS Pro LLC, Innovative Microwave Solutions Prototype. And that's Christos and me visiting her lab. This is a phase 2 SBIR project for AFRL. She built everything herself, everything from the pulse power to she designed the microwave source, and she's the one, her PhD dissertation was showing the breakthrough we made in the magnetron. Finally, last but not least, Stacy Hernandez, who's here today in the audience. Stacy's family is originally from Sinaloa, Mexico. And Stacy has very interesting stories of when she was driving to Sinaloa with her family after El Chapo was captured. But she also took undergraduate electromagnetics with me, and I recruited her to work in my lab. She worked in my lab. And then she did her PhD. She did her PhD research at Sandia. And her work at Sandia, her PhD dissertation was trying to understand current flow in the Z machine. So you have 80 terawatts of electrical power, and you have all these strange convolutes and things, and her PhD was trying to improve the ability to measure current. And last year, she won the Robert J. Barker Graduate Student Award. Also, Robert J. Barker passed away in 2014. He was the program manager at AFOSR that took the chance on me and gave me my first award back in 1989. She also won the Best Paper Award at the Berlin Conference last summer, and she's a postdoc currently at Sandia. Okay, acknowledgements, lots of funding agencies, thank you. It's all my students, postdocs, and research professors. I'm just the conductor of the orchestra. Colleagues and collaborators, we've had a very strong group of faculty who came to UNM. When I came, Ramiro Jordan was already here, and we all became very good friends. I came in January '88, Chowki Abdullah came in August of '88, and we were like brothers. We all grew up together. Our children grew up together. And the key thing is we always fought to make the ECD department and UNM better. That was our goal. And then we engineered bringing Christos here in 1999 as our department chair, because Greg Heilman knew Christos from UCF, and he said, Christos would be a great chair, and this and that. So that's how. And of course, I thank my colleagues, collaborators. I thank my family, of course, my wife, Elmira. We met in 1981. We got married in 1983. So she's been on this journey with me. I'd like to thank my brother and my cousins and all that. And this is our daughter, Celine. And she got her PhD at UC San Francisco in 2023. We're very proud of her. She's a postdoc at Anschutz Medical School in Denver. And she and her husband, Arturo, have been fabulous. Finally, to wrap things up, for New Mexico Economic Development Directed Energy, we have all these labs in New Mexico. We have large industry. We have all these smaller businesses. And so directed energy is an important contributor to economic development in New Mexico. Fusion. So many of you have heard Pacific Fusion, which is from the Bay Area in California, is building $1 billion facility at Mesa del Sol. They're going to build this machine here. And this does things very similar to what the Z machine does at Sandia, except much more power, much larger currents. A couple of weeks ago, it was announced that Fuse is opening a facility in New Mexico. And Liberty Fusion is a spinoff from Los Alamos, and they're building a lab in Santa Fe. So who will train the next generation workforce for New Mexico directed energy and fusion? It's the University of New Mexico. So thank you for your attention.
Thank you, Edel. What a wonderful talk. Thank you. We do not have a Q&A for this because we have a wonderful reception where Edel will be taking all of your questions and answering them as well with a glass of wine. And hopefully it's good enough to pass the Edel test. We'll find out. I do want to bring up Tito Busani, Associate Professor in Electrical and Computer Engineering and Chair of the Research Policy Committee. Tito currently, today, right now, has the job that I do not envy, which is to keep you all from the reception. So you are the one thing standing between us and great food and hopefully great wine, Tito. But
and it won't take a minute. So I want to, technically I'm representing the Faculty Senate tonight. And so I hope Professor Shimogogo allows me to call you Edel, much easier. My name is easy, Tito. And first of all, I want to mention that the award, there are 3 components of the award: the esteem that we have for you, the physical award that you can see here. And you see, you're keeping people away from it. And there is also a money award. And thank you to the VPR, Ellen, and VPR Hengame. And also there is, your name will be outside the VPR office, if I'm not mistaken. There's a little bit of plate, if I'm not mistaken. So this is physically what happened when we give these awards. There's a lot of work. I wrote something and I prefer to read, if you don't mind. And but one thing I want to say about Edel, personal experience, kind of his personal experience. Since everybody says anecdote tonight, I was communicated to me by another faculty, which I trust the faculty is not here anymore. There was and I was not in that faculty meeting. And one time there was a debatable case about a professor, sometimes funding goes up and down. And the chair of the ECE was telling the faculty how to move the research he or her was doing. And Edel stepped in academic freedom, telling you hire this faculty for the research that this faculty wants to do. And it's about the faculty to choose the research that they want to do. So that's embodied the symbol of academic freedom, and is a symbol also of the Faculty Senate, the academic freedom that we have at UNM. Fortunately, we still have it. Edel has been part of the UNM and the New Mexico community for so long that his impact is woven into the fabric of this institution. He has been an extraordinary contributor not only through his research, but through his dedication to students and his commitment to outreach. His influence extends well beyond campus, shaping the broader New Mexico ecosystem. I won't repeat what Christos, I won't say the last name, Christos, if you allow me, what Christos said, already shared. Nor I will attempt to paraphrase Idol's own inspiring talk. Instead, I would like to take a moment to reflect on the significance of the award that he is receiving today, because today is about Idol's career, of course, but it's also about the award and the annual research lecture award that he's receiving tonight. This is one of the most important recognition, as Ellen, thank you, Ellen, sorry, I say Ellen, UNM offers to its faculty, honoring those who have made substantial contribution in research, local, national, and global levels. This is one of the most, this is not an award one receives early in a career, even with outstanding work. It is not simply a recognition of excellence in a moment. It is acknowledgement of leadership over many years, often across a generation or more, of building international connection and being deeply embedded in the UNM community. Personally, I make this statement, for me, this award is like the Nobel Prize of UNM, fought not the same amount of money of the Nobel Prize, sorry for that. We are a little university. You might wondering why I'm speaking about the award itself. I was introduced, thank you very much, as an associate professor, and I'm the chair of the Research Policy Committee, a faculty committee that within its duties also review the nomination and the nominees for this award and makes recommendation. I emphasize it is a faculty committee of the university, not just a committee of experts in a field. The committee is composed of faculty from across discipline, engineering, science, art, humanities, library, health science, and UK, Anderson, School of Business, and so on, representing the full breadth of UNM mission. We also reviewed the CRL Award, and tonight I see in the audience the person that has been nominated for the CRL Award for this year, which in spirit, I would say, is like the MacArthur Fellowship with less money, of course. It is a challenging role, maybe yes, maybe not. It is a rewarding role to see all these applicants and the contribution they did to UNM. What makes this award meaningful is not just the fact that the person is recognized for the quality, it's a statement, in my opinion, of belonging as much as a statement of achievement. While the Faculty Senate and the Research Policy Committee established the guideline and reviewed the nomination, these awards would not be possible without the support of Vice President for Research, Ellen, and the Vice President of Research of main campus, Hengame. I would like to acknowledge VPR Fisher and VPR Hengame for fostering a constructive and collaborative dialogue with the committee. I also to thank Associate VPR Perumal and Associate VPR, and if you think now Shimagolo is complicated, here this one, my good friend, Associate VPR for HSC, Retlefen, I can't pronounce her name, she's a good friend, I apologize. As an official member of the committee, they bring valuable perspective, thoughtful feedback, and a spirit of collaboration that strengthen our work, something that truly makes a difference. I also want to thank you, Melissa Emery Thompson, Assistant Vice President for Research. I know this event would not be possible without her. I greatly appreciated our conversation, her insights, and her commitment to promoting the CRL Award and the ARL Award. Thank you, truly. Now, 1 minute and I will be done. Let me close it with a final remark. If these awards are meaningful and prestigious, as I described, and I know you believe in that, and I know you know that, then it's our responsibility as a community to recognize our peers. So I invite you all, nominate your colleagues. We have many outstanding faculty at UNM who deserve this recognition. Let's make sure their contributions are seen and honored. And that's all. And now the second best part of the award, the reception. Thank you, Ido.